So, permutations and combinations basically is going to be talking about counting. How many different ways can things occur? So, one example would be how many different test responses are possible for a test consisting of 10 multiple choice questions with each with 4 possible answers. So, if you're guessing on every question, how many different potential guesses could a person have, or how many different uh, responses could be given for that test? How many different QR codes are possible? So this can be answered using what we're going to be learning about in this chapter. How many different license plates are there? If you can have any 3 letters followed by any 3 digits, and there's no restrictions on which letters or digits you may use. So that's something else that we will be seeing in this chapter. So we're looking at a branch of mathematics called combinatorics. It's a branch of discrete mathematics. It can be defined as the art of counting. Famous links to combinatorics include Pascal's triangle, which we're going to talk about, something called the magic square, Koenigsberg bridge problem, Kirkman's schoolgirl problem, and Miriorama cards. So those cards were invented in France around 1823 and further developed in England. Each Mirioramas were decorated with people, buildings, and scenery. So they were cards that were decorated with people, buildings, and scenery that could be laid out in any order to create a variety of landscapes. 124 card set is sold as the endless landscape because of the number of different arrangements that could be done. And that number is 6.2 times 10 to the 23. So 6, 2, then 22 zeros after it. So that would be the number of arrangements of any combinations of 1 to 24 of those cards. So not only are you changing how many cards are selected, but also the order that they are arranged in. Okay, Adil? So you're just calculating that, right? Yeah. Okay, so big number. We'll see where that number would come from. So as a warm-up, you just want a trip to San Diego for the weekend, but you can only take a carry-on. You pack 3 t-shirts, 1 black, 1 gray, 1 white, 2 pairs of shorts, 1 red, 1 white, and I know you're wondering who would wear red shorts, but that's just a question. And 2 pairs of sandals, 1 black and 1 gray. How many different outcomes are possible? So you might guess. How many different outfits could a person select? You're going to select 1 shirt, 1 pair of shorts, 1 pair of sandals. How many different outfits could you come up with? So we're going to see there's a couple different ways that we can figure out what that answer is. And one would be by using a tree diagram. So let's start with the shirts. There are 3 options for shirts. There's black, there's gray, and there's white. And for each shirt that a person chooses, there are 2 possibilities for the shorts, either red or white. For each choice of shirt, you have 2 options for the shorts. And then, for each choice of shirts and shorts, you have 2 choices for the sandals, black or gray. So I'll write BL for black and then G for gray. Let's put this. So if you count up all the BL and Gs on the bottom, there are a total of 12. So one possible outfit would be black shirt, red shorts, black sandals. That's one possibility. Or black shirt, red shorts, and gray sandals. That's only two of them. If you count up all of the BLs and Gs on the bottom, that will be the total number of outfits that are possible, which would be 12 outfits. So a tree diagram would work. And it's a reasonable way to do this one if you wanted, because 12 isn't a big number, right? But you can imagine if you had 5 shirts and 7 pairs of shorts and 2 pairs of sandals, how much bigger that tree diagram would be. The nice thing about the tree diagram is we can actually see what the different possibilities are. But in many cases, you're just going to want to know how many different possibilities there are. So is there an easier way to do this? So in this case here, again, we had 3 t-shirts, we had 2 pairs of shorts, and 2 pairs of sandals. And together we got an answer of 12 different outcomes or outfits. What can you do to those 3 numbers to get 12? Well, obviously you can multiply them. 3 times 2 times 2 will give you 12. So if you just want to know how many different possible outfits this person could select, you just multiply those numbers together. If you want to know what the different outcomes are, then the tree diagram could be used. So this illustrates what's known as the fundamental counting principle. If one task can be performed in A ways, a second task in B ways, then the 2 tasks can be performed in A times B ways. For example, a restaurant meal consists of 1 of 2 salad options, 1 of 3 entrees, and 1 of 4 desserts. So if you multiply 2 times 3 times 4, it'll give you the number of possible meals that a person could order, 24. So this is known as the fundamental counting principle, and it's a strategy that we can use as we go through this chapter. A Math 30-2 quiz consists of 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? So because there are 8 multiple choice questions, I'm going to mark down 8 spaces. And each space has 4 possible choices, A, B, C, or D. So when we're using this fundamental counting principle, we'll always start by writing down our spaces. And as we've seen, the fundamental counting principle says you're going to multiply these numbers together. So you could write it like that, or you could also write it as 4 to the power 8, because you're multiplying 4 by itself 8 times. And so 4 to the power 8 is 65,536. So that's how many different possible answer sheets could be filled out. If you were guessing at everyone, that's how many different possible answer sheets could be filled out. An online game asks you to create a password. It must be 4 characters in length, and you can use any lowercase. So there's 26 lowercase letters, any uppercase, so there's another 26 for the uppercase, and any digits. There are 10 digits, 0 through 9. So this gives us a total of 62 characters to choose from. How many passwords are possible if you may repeat any character? So again, it has to be 4 characters long, so let's mark down 4 spaces. And as we said, 26 and 26 is 52, plus 10 is 62. There are a total of 62 characters that you can choose from. And part A, we want to know how many passwords are possible if you can repeat characters. So this would be 62 multiplied by itself 4 times, or 62 to the power 4. Either way, this will be the number of passwords that are possible. So big number, over 14 million. 14,776,336. Part B, though, says, what if you are not allowed to repeat any characters? So this would mean that you'd have 62 choices for the first character, but then 61 for the second, then 60, then 59. So 62 times 61 times 60 times 59. So there's going to be fewer possible passwords if you're not allowed to repeat a character. Just over 13 million. 13,388,280. So as we go through this, we're going to be talking or seeing examples where you have some restrictions. And this is how we deal with those restrictions. They're going to affect the number of choices you have in each space. Number 3 says determine the number of distinguishable 4-letter arrangements that can be formed from the letters of the word English. So that word has 7 letters, but we're only going to use 4 at any time. We want to know the number of 4-letter arrangements from the letters of the word English. And so for part A, it says there are no restrictions. So because we're only going to be arranging 4 letters, we mark down 4 spaces. There are 7 letters in the word, so there'd be 7 choices for the first. Now, you have to think of this like Scrabble tiles, meaning there's no repetition. Once you use a letter, it can't be used again. Okay? So that means there'll be 6 choices for the next letter, and then 5, and then 4. Again, this is like you've got the letters, you're cutting them out if you want, you write them down, you're cutting them out, or like the Scrabble tiles. Once you use a letter, it can't be used again. So 7 times 6 times 5 times 4 gives us a total of 840. So now what about if we have some restrictions? Part B says, what if the first letter must be the letter E? So we're still arranging 4 of the 7. So we'll mark down 4 spaces. However, in this case, there's only one choice for the first letter. It has to be an E. One choice. We started with 7. We've put the E in the first position. Now we have 6 choices for the second letter. And then 5, and then 4. So 6 times 5 is 30, times 4 is 120. So quite a few fewer possibilities when we have that one restriction of what the first letter must be. Now, part C says, what if the arrangements must contain the letter H? So we're going to see as we go through this, in some cases we have to look at different scenarios. So, the different scenarios would be that the first letter is the H, or the second letter could be H, or the third letter could be H, or the fourth letter could be H. And again, this represents different scenarios. We can have one, or the second, or the third, or the fourth. So, if the first letter is an H, you're going to have one choice for the first letter, then 6 times 5 times 4 for the remaining, like we did in part B. That gives us 120. 120 different arrangements if the first letter is the H. Now, what if the second letter is the H? Now we'd have a 1 for the second space. The second letter is the H, so there's only one choice for that. We started with 6 letters. We've used 1. Sorry, we started with 7 letters. We've used 1, so now we have 6 choices for the first letter. We already got 1 choice for the second. We'll have 5 for the third and 4 for the fourth. So that's also 120. What if the third letter is the H? So you'd have a 1 for that third space. We started with 7. We've already set the H in the third space. So now we have 6 choices for the first, 5 for the second, again 1 for the third, 4 for the last. That also equals 120. So it's also going to be 120 for this last scenario, where the H is in the last position, so we put a 1 there. The other spaces are 6 times 5 times 4, which is 120. And so what do you think you would do to all these 120s? You'd add them, right? Add them together, which is 480. So when you have these different scenarios and we're using the word or, you're going to add the scenarios together. The word and means to multiply, and that's what we've been using with this fundamental counting principle. If we look at question A, you have 7 choices for the first letter and 6 choices for the second, and 5 for the third, and 4 for the fourth. The word and means to multiply. The word or means to add. Part D says, what if the first and last letters must be vowels? So vowels are A, E, I, O, U, and Y. If we look at the word, there are only 2 vowels, E and I. The first and last letters must be vowels. So it doesn't really matter if you start with the first letter or the last letter. It doesn't matter. Let's start with the first letter. If it must be a vowel, there's 2 choices for that first letter, either the E or the I. But once you select one of those, it only leaves you with 1 choice for the last position. Right? If we would have started with the last position, that would have been the 2, and the first position would have been the 1. So you're still going to multiply by 2 and 1. You started with 7 letters. You've now used 2 of them. That leaves us with 5 remaining when we choose the second position, and then 4 when we choose the third. So that gives us 40. 40 different possible 4-letter arrangements using the letters of the word English, where the first and last must be vowels. So you're seeing that as we're doing this, if there's restrictions, we always deal with those restrictions first. Number 4, in how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at the end of each row? So in this case, you're going to seat all 7 of the students. There are 4 girls and 3 boys, and a boy must be seated at the end of the row, which means you would have 3 choices for the first position and then 2 choices for the last position. There are 3 boys to choose from. So you need a boy at the start and a boy at the end. You started with 7 students. You've used 2 of them. Now you have 5 remaining to start filling in the other spaces. And obviously, once a student is seated, they can't be picked up and moved somewhere else. So we're always decreasing the number of possibilities as we go from space to space. So we've got 3 times 5 times 4 times 3 times 2, and we can multiply by 1, but that's not going to change anything. But then we also have that 2 at the end. So that gives us a total of 720. 720 different arrangements of those students if a boy must be seated at the end of the row, at each end. How many 5-digit numbers can you make using those digits? And it says in this case, repetition is allowed. So we're going to create 5-digit numbers, and there are 5 digits to choose from. If repetition can be allowed, you've got 5 spaces, and there's 5 choices for each space, so the answer could also be written as 5 to the power 5. Which is 3125. What if repetition is not allowed? Does it change the answer? Well, it's going to definitely change the answer. Because you'd have 5 choices for the first, and then 4, and then 3, and then 2, and then 1. So there's going to be fewer answers. Now, that expression could be written as 5 factorial. That's what factorial means. Factorial is an exclamation mark after the number, and it means you start with that number and then you multiply by 1 less than the original number times 2 less than the original number times 3 less than the original number, and you keep doing that pattern until you get down to 1 at the end. And there's a factorial key on your calculator. So you're going to put the 5 in first. Well, first let's see what we get. 5 times 4 times 3 times 2 times 1. Whoops. Try that again. That should be a times. There we go. So the answer is 120. Well, you can get this using the factorial mode in your calculator. So you're going to go 5 first. Now to get that, you're going to go to math. The math key is below the alpha key. It's in the 3rd row on the left-hand side. And you're going to slide over to probability. You see number 4 in this list is the exclamation mark. So you can scroll down, or you can just hit 4, and it puts that exclamation mark in there. That's factorial. When you hit enter, your calculator will multiply 5 times 4 times 3 times 2 times 1. It just saves you typing all those numbers in. Okay, so in general, n factorial is n times, like I talked about earlier, n minus 1. It's times the number 1 less than the original, times the number 2 less than the original, and you keep going until you get down to multiplying by 3 times 2 times 1, where n is an element of natural numbers. See, we're talking about counting. How many objects can you arrange, or how many objects can you select from? So n can't be negative, can't be an integer, all integers anyways, and it can't be 0 either. You can't select from 0 numbers. However, it does say that 0 factorial does equal 1. That is on the formula sheet, and we will see why that is true. So we've been talking about arranging objects or people in a line. This is called a linear permutation. With a permutation, the order of the objects is important. When objects are distinguishable from one another, a new order of objects creates a new permutation. So a permutation is an arrangement or sequence of all or part of a set. That's what we have been doing. today. We have been doing permutations. Permutations are used when order matters. When you change the order, do you get a different arrangement? That's a permutation. That is different than a combination. A combination is where items are being selected, but the order that they're arranged doesn't actually matter. So I'll give you an example. Let's say that students are running to be on the grad council, and there are positions. There's a president, there's a vice president, and there's a secretary. The order these students are selected matters. They hold different positions. That would be different than if you have a grad committee of 3 and they all do the same job. They're all working together on this committee. Now, in that case, order doesn't matter, right? That's a combination. But if order matters, that is a permutation. So as we go through this chapter, we're going to be asking ourselves, does order matter or does it not? If it does matter, that's a permutation, and there's a way to do that. One of those ways is the fundamental counting principle. If it's a combination, there's a different way to do that. We're also going to see that there's a different way to do permutations instead of using the fundamental counting principle. Okay, we'll get to that. Number 6, it says evaluate without using the calculator. So here's how we can do that. We can expand the 10 factorial. And the reason I'm going to expand that is because 10 is larger than 8. When we expand these, we're always going to start with the largest expression, which in these cases would be the largest number. But when we look at question 7, they're not numbers, they're expressions. But we're still going to expand the largest expression. So back to question 6a. I'm going to expand 10 factorial. So it's 10. The next number would be 9. And we can keep going all the way down to 3 times 2 times 1. But I'm going to stop at 8 as my last factor when I expand this. The last factor always has a factorial on the end. And the reason I stop there is because that's what the denominator is. The denominator is 8 factorial. Because the top is in factored form, I can cancel. I can divide top and bottom by a common factor, which would be 8 factorial. They cancel, and you're left with 10 times 9, which is 90. So we were able to do this without even using a calculator. We can check to make sure that that is correct by going 10 factorial divided by 8 factorial in our calculator. And we do get 90. So it checks. It checks. So we can do the same thing with question B. Again, I'm going to expand 7 factorial. That's 7 times 6. And I can keep going as long as I want, but I'm going to stop at the 4. And whatever the last factor in the expansion is, you put a factorial on the end because that is our denominator. Our denominator is also 4 factorial. And once again, we can divide top and bottom by common factor of 4 factorial. And we're left with 7 times 6 times 5. Well, 6 times 5 is 30, times 7 would be 210, which we can check on our calculator by going 7 factorial divided by 4 factorial divided by. So there we get that answer. So to simplify these expressions, we'll use the same process. We'll expand the larger expression. N is bigger than n minus 3. So we'll expand n factorial. The first factor will be n. The next one will be 1 less. And we'll keep going. We're going to stop at the n minus 3. And again, the last factor in the expansion always has a factorial on the end because that's our denominator. Our denominator is n minus 3 factorial. And we can divide top and bottom by n minus 3 factorial. We are left with n bracket n minus 1, n minus 2. There's the simplified expression. We can do the same for question B. We'll expand the larger expression, which is n plus 4. that's our first factor. The next factor is 1 less, which will be n plus 3. So you need to get to the other factor, or in this case, the denominator. So we're going to stop at the n plus 2, and whatever the last factor in our expansion is, we put a factorial on the n, because that's our denominator, and they will cancel. And so our simplified expression would be n plus 4 bracket n plus 3. So we can use that process to solve a question like number 8. There have been questions similar to this on diploma exams before. They would say determine or algebraically determine, which again means, remember, that you have to show your work. So we would solve this by expanding the larger expression, which is n plus 2. And in this case, we only have to put 2 factors, because after n plus 2, the next term or the next factor in the expansion is 1 less, which would be n plus 1. We would stop there and put the factorial in the end, because that is the denominator. So the n plus 1 factorials cancel, and we're left with n plus 2 on the left equaling 6 on the right. Subtract 2 from both sides, and n equals 4. And we can check this. Again, if we start with the original equation, n plus 2 factorial over n plus 1 factorial must equal 6. So when n is 4, you'll have 4 plus 2 factorial over 4 plus 1 factorial. So that'll give us 6 factorial over 5 factorial, which does equal 6, because 6 factorial will be 6 times 5, and we could keep going all the way down to 2 times 2, 2 times 1, but I will stop with the 5 factorial and put a fact, because that is the denominator. So the 5 factorials will cancel, and you get 6. You get the same thing on both sides. So that just shows that our answer of 4 does work. Okay, tomorrow we'll look at some examples like this where we're going to again end up with quadratics that we have to solve. Okay. All right. Would be assignment that you should work on. Actually, it's in the book. 11.1 assignment should be the next thing in the book. Yeah. So I will post the solutions to this on Google Classroom so you can check your answers. Okay. So you should